Hey everyone, welcome to the class 3 of Deep Learning 2020. In this video, we are going to build our first deep learning neural network. Now, recalling from the last video, we have learned that there are 5 parts in any machine learning model. So, we have learned as the 5 parts are data, task, model, learning algorithm and loss function, and then evaluation function. Now, based on the data, we will be deciding the task that we are going to perform. So in our case, we are going to make use of MNIST dataset. To begin with, I'll start by importing the necessary library. In this course, I'll be making use of the TensorFlow 2.0. So I'll start by importing like this. So I'll write as import TensorFlow as TF. So this will import the TensorFlow. I'll display the version of it. So I can write as tf.version. So the version that is available to me is 2.2.0. Okay, we have imported the library. Now, as a next step, what we have to do is we have to decide on the data. As I said already, we are going to make use of MNIST dataset. Now, what is this MNIST dataset? So this is the page of official MNIST database. So it says it is an MNIST database of handwritten digits and it has a training set of 60,000 examples and has a test set of 10,000 examples. So if we open the sample images of MNIST, it will look like this. So these are the samples of MNIST database. It contains the handwritten digits. So as you can see, we have the handwritten digits between 0 to 9. So this particular column shows the 0 and this has 1, 2, 3, 4, 5, 6 up to 9. So the task for us is I'll have to identify whether this particular image, in this case, if I select a particular image, let's say this one, then my task will be, if I have this particular image, then I'll have to classify this image to be belong to the class 0. In the same way, if I have been given the task to what is the classification of this particular digit, let's say this particular image, this one, then my task will be to identify to which class this particular image belongs to. In this case, it is 6. Similarly, if I have been given to find what is the classification of an image which belongs to this, that is which looks like this, then my task will be assigning the value 4 to this image. So if I come back to this slide, the 5 parts of machine learning program, I have the data as MNIST dataset. Now, by looking at the data, I can say the task that we are going to perform is classification, because I want to classify the output label into one of 10 labels. See, the 10 labels are 0 to 9 and I'll have to classify each image into one of 10 labels. So the task is classification. Now coming to model. In case of machine learning, we'll be selecting a single model which says linear regression, random forest or any other model. But in case of deep learning, as we have learned in class 1, deep learning contains a series of neurons which are connected together in the form of a network. It will have an input layer and it will have the hidden layer as well as it will have an output layer. The input layer takes the input, the hidden layer processes the information, and output layer will give the output from the neural network. So let's build a neural network and understand more about this particular dataset. To begin with, let's start by loading the data. So I'll load the data like this. This particular MNIST database is available inside the TensorFlow itself. So I'll write it like this. So to import, I'll write as from tensorflow.keras.datasets import MNIST. So this will download the MNIST object, and then okay, there's an error. Okay, this has loaded the MNIST object. Now I'll separate the training images and the test images like this. So I'll write as train images, comma, train labels, then test images, comma, test labels is equal to MNIST dot load underscore data. So this will download the data and assign the training images and the training labels to these two elements in the tuple, and assign the test images and the test labels to these two variables inside the particular tuple. So what we can do is, let's verify the size. Okay, so I'll write it like this. So train images dot shape. So the shape of the training images is 60,000, 28, 28. That means each image is of the size 28, 28, and I have 60,000 such images. To give you more clarity, so if you see this particular example, I have around 100 images. So like this 100 images, in our training set, we have 60,000 different images. If I display an individual image, so let's say train images 0. So this is the first image from the data set, and shape. So I have the output as 28, 28. That means each image is of the shape 28, 28, and in train images I have 60,000 such images. If I look at the train labels which are associated at index 0, then the value is 5. That means the image which is at first position in the train images is having the label of 5. So if I print as length of train images, so this is 60,000, and length of train labels is 60,000. That means each image has a single label. Got it? Cool. Now moving on to the test data. So if I display the shape of test data, so test images dot shape. So this is of shape 10,000, 28, 28. That means we have 10,000 images in the test data, and each image is of the size 28, 28. So in the same way, the length of test labels will be 10,000. See, this is 10,000. So what we have done is, we have imported the TensorFlow STF, and to load the datasets, I have made use of TensorFlow.keras.datasets, that is MNIST object. And to load the dataset, I have called the function load_data. And then I have performed the split between train and test data. And actually this is not the split. I just separated the training data and the test data. And after separating the training data and the test data along with its images and the labels, I have the resulting shapes of train images as 60,000, 28, 28, and the train, that is individual images, is of the size 28, 28. And in the same way, I have 10,000 images in case of test images, and each image is of the size 28, 28, and the length of test labels is 10,000. So we have loaded the dataset for our working. np.max. So this time I'll give as train images 0. In the same way, I'll give as np.min train images 0. That means I'm checking what is the maximum value that each image has, and I'm also checking what is the minimum value that each particular image has. Since this is a black and white image, I have the values between 0 to 255. Now what we will do is, as per data pre-processing, we will divide the entire train images and the test images by 255, such that the resulting values would be between 0 to 1. We are doing this because, see, if you see here, like we have the values ranging between 0 to 255. Then like when we apply the deep neural network which has many number of neurons, then in that case the values may simply go high. To avoid that, what we will do is, we will normalize it by dividing by 255 such that the values would range between 0 to 1. So to do that, I'll just write it like this. So I'll write as train images is equal to train images dot as type float divided by 255. In the same way, I'll write as test images is equal to test images dot as type float divided by 255. So I'll just set it as float 32. Okay. This has been completed. Now if we check the minimum and the maximum in each particular image, I can see the maximum is 1 and the minimum is 0. That means all the values are normalized for individual images. Now another pre-processing step which we do when we are applying the deep learning is converting the images which are in the form of matrices into a single long vector. To do that, we know already we can make use of the reshape function. So since we have 60,000 images, I'll reshape the 60,000 images like this. So this time I'll write as train images is equal to train images dot reshape 60,000 28 multiplied by 28. In the same way, I'll write as test images is equal to test images dot reshape 10,000 comma 28 into 28. Okay, this has been done. Now if I print the shape of the first image, that is train images 0 dot shape, this is of the shape 784 comma blank. That means this is a single dimensional vector, that is single dimension array, which is of size 784. Got it? That means the entire train images is of the size 60,000 comma 784. This is because the individual images which was of the size 28 comma 28 has been reshaped into a single dimensional vector. Hence here I have mentioned as 28 into 28. Okay, so we have pre-processed the data by dividing it by 255 so that the values would range between 0 to 1, and then we have reshaped the data into 28 into 28. That means we have converted individual image which are in the form of rows and columns, that is which was in the form of matrices, into a single long vector. Okay, now let's do the another pre-processing step for the labels column. Now what I'll do is I'll write it like this: np.unique train labels. So if I give as np.unique train underscore labels, we can see the labels, the different labels which are present are 0 to 9. In the same way, if I write as np.unique train test underscore labels, we have an array which has the values between 0 to 9. That means my train label and the test labels has the classification labels as 0 to 9. As a part of pre-processing step, what we will do is we will convert these labels into one hot encoding. Now what it means is, like, let's say if I have the columns like this. So this is an example of the classification problem. Let's say if we have the column labels as red, yellow and green. As you can see, the red has repeated twice. So the red has repeated twice, and we have an yellow here and yellow here, and we have a green here. So this is an example of a classification problem. Now what we will do in case of one hot encoding is that we will put all the unique values in the output labels as individual columns in a matrix, and then whichever the value is present for that particular line, we will mark as 1. If you see here, in first case the label is red. Hence, if you see in the first row here, on the red value is marked as 1. In the same way, for the second row, we have it as red. Hence I have marked as 1 in the column red, and rest I have marked as zeros. And on the third row, I have the value as yellow. Hence, in my one hot encoding box, I have mentioned as 1 for the yellow column. In the fourth row, I have the value as green. Hence, in my one hot encoding, I have mentioned as 1 for the green column, and remaining all the columns as 0. Now to convert this particular label data which we have into the categorical vector, we convert it with the use of inbuilt toCategorical function. So I'll write as .keras.util import toCategorical. So after importing the toCategorical function, we will just convert the train labels and the test labels into one hot encoding vectors like this. So I'll write as train underscore labels is equal to toCategorical in the same way. I'll write as test underscore labels is equal to toCategorical test labels. So what this will do is, this will convert the train labels and the test labels into one hot encoding vector form. Now after converting it into one hot encoding form, if I write as train labels of 0, then we have the one hot encoding vector like this. As you can see, we have 10 zeros. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is of length 10. Now we have a value of 1 for one of the index. So let's check that index number. So the index is 0, 1, 2, 3, 4, 5. So for the fifth index number, we have the value equal to 1. That means the label which is referring is to the value 5. To verify this, I'll open the screen which I had already opened. So if you see here, yeah, I had displayed the train label which was at index position 0. So it had the value of 5. Hence, this value 5 has been converted into one hot encoding vector of the form like this. So all the values equal to 0 except for the value at index position 5, which is equal to 1. Got it? So we have done two things as a part of data pre-processing. So first is we have normalized the data and reshaped it, and second is we have converted the output vector into one hot encoding vector. Okay, so with this we are done with the two important tasks of the machine learning or any deep learning, that is data and task. So the task we have is the classification, and the data which we are using is an MNIST database, and it is a classification problem, and we have pre-processed the data as per our requirement. Now as a next step, let's build our first deep learning neural network model. So to create the deep learning neural network model, I'll write it like this. As a first step, I'll import the models and layers as from tensorflow.keras import models. In the same way, from tensorflow.keras import layers. So this will import the models and layers from tensorflow.keras. And then I'll instantiate the model as network is equal to models.sequential. So what it means is, like, I'm trying to create a model which is of sequential pattern. That means which are stacked one next to another. So if you see the diagram here, I have the layers which are stacked one next to another. So I have the input layer, and this is stacked with another hidden layer, and this is stacked with another hidden layer, and this is again stacked with another hidden layer. Hence, I have written a neural network which says models.sequential. And then after defining the models as sequential, I'll add individual layers. For the first layer, I'll write as network.add. That means I'm adding an individual layer to my existing sequential model. So network.add layers.dense, and inside the parenthesis, I'll write as, here see, the first parameter is units. For the number of units, I'll write as 5. For activation, I'll write as ReLU, and then I'll input the input shape as 28 into 28, which is a single dimensional vector. Got it? So here what I'm doing is I'm adding a new layer to my sequential model, and this is of the type dense. Dense means fully connected deep learning network. If you see here, can you see, like, the red dot is connected to all the green dots, and each individual red dot is connected to individual green dots. In the same way, each individual green dot is connected to all the blue dots which are in the next layer. That means it is in the form of dense. So that is what I'm saying here. I'm saying as layers.dense, and then for the number of units, I'm mentioning it as 5. That means I'm having 5 units of neurons in this particular layer. And this takes the input which is of the shape 28 into 28. That means 784 comma blank. That means a single dimensional vector which is of shape 784. Why? Because this is same as the individual shape image that we have. Got it? So after adding this first layer, I'll add a new layer as network.add layers.dense. That means I'm adding one more dense layer, and this time it has 10 units. and this time it has the activation as, let's say, another ReLU. And after this I'll add one more network. So this time I'll write as network dot add layers dot dense, and for the I'll consider it to be a last layer. So for this layer I'll write as number of units to be equal to 10 and activation is equal to softmax. Now I'll stop here because I have defined it to be an output layer and I have set the number of units in output layer to be equal to 10. This is because I want to classify each input that I have, that is in case of each image which is of the shape 784 comma blank, that is 784 items. I want to understand the values present in each image and I have to classify into one of 10 classes. Hence in my output layer I have mentioned as 10 units. So I'll repeat this again guys because this is very important. First, I'm initializing my network to be of sequential. After initializing my network as sequential, I'm adding the individual layers. In my first layer, I have added 5 units and this has the activation as ReLU. And for that, I have also specified the input shape to be equal to 28 into 28. That means 784. I have added a dense layer with 10 units and activation function as ReLU. And in the final layer, I have added 10 neurons, that means 10 units of neurons, and with the activation as softmax. The reason I have added softmax because the output that I get from the softmax activation function will be the probability distribution between 10 values. Since the output layer has 10 neurons, I get the probability distribution of 10 values. So in my case, if I input the image presented index position 0, then in that case, I get the probability for the value 5 as highest. So with this, we have defined a neural network. So this particular third part is complete for the deep learning. Now the next step would be defining what will be the learning algorithm, loss function, and the evaluation metric for my deep learning network. To define that, we will make use of compile function. So to compile a neural network, we will write it as network.compile, and inside the parenthesis we will define the parameters. So for the first parameter learning algorithm, I'll write as optimizer is equal to, I'll write as RMS prop, and for the loss function I'll write as categorical cross entropy, and for the metrics, that is evaluation, I'll write as accuracy. So with this, we have defined 5 parts of any machine learning model. So I have the data and I have decided the task to be classification, and I have defined my neural network with 3 layers. So the first layer has 10 neurons with the input shape as 28, 28, 28 into 28, activation as ReLU. And in second layer, 10 neurons with activation as ReLU. And in my final layer, I have 10 neurons with activation as softmax. So I have defined my model, and the learning algorithm is RMS prop. Loss function which I'm using is categorical cross entropy, and the matrix is accuracy. Got it? Now I'll compile my network. Now I'll fit my model. So for that, I'll write as network.fit, and inside the parenthesis I'll define as, I'll write train labels. So first train images, that is for X it is train images, Y means train labels, batch size I'll give as 64, and epochs I'll give as 5. So train images, and the Y I'll write as train labels, and for batch size, like I said, I'll give 64, and epochs I'll give as 5. Okay, I'll execute this. Okay, this will take some time based on the system performance. Oh, awesome guys. Okay, it's performing well. Okay, the execution has been completed. So now let's perform the evaluation on the test data. So I'll write as test underscore loss, test underscore accuracy is equal to network.evaluate, and I'll pass the test images. test labels. Okay, this is done. I'll print the test accuracy is okay, we have the test accuracy as 86.59%. Well, with the first deep neural network that we have built, I think this is one of the best, guys. So we'll try again and we'll learn more as how to perform better and how to get the more accuracy in a deep neural network. But I hope you now have an idea as how to build a deep neural network using TensorFlow. To summarize, what I've done is I've first imported the TensorFlow as TF, and I've just verified the version, it is 2.2. And then I have loaded the dataset MNIST. After loading the dataset, I have separated the train labels and the test labels along with its images. So I have separated train data and the test data. And while splitting between training and test, I have also splitted as images and labels the images of the shape 28,28, and total we have 60,000 images, and we have 10,000 images in test. And we have done some data pre-processing, so the maximum value is 255 and the minimum was 0, hence we divided the entire training data and test data by 255 such that the value would range between 0 to 1, and we could verify it here. And after that we have reshaped into a single long vector, so that means each individual vector which was in the shape of 28,28, and we have converted into 60,000 into 784. That means we have converted the image which was in the form of 28,28 into 28 into 28. That's it. And after that, what we have done was we have created one hot encoding of the output vector. So in our case, we had the unique values as 0 to 9 in case of both training labels and the test labels. So what we have done was we have made use of two categorical function which was present inside the tensorflow.keras.utils, and we applied the two categorical on training labels and the test labels. And after that we could verify that the labels, that is each training labels and test labels, has been converted into one hot encoding vector. So we can verify it over here. So if I give as train labels dot shape, so this will have the shape as 60,000 into 10. See, this is because each individual value which we had previously has been expanded into a vector which is of size 10. So the individual value which we had before was 5, and this is how it looks like after converting into a one hot encoding vector. And after that we defined our model. So we have defined our model to be sequential form, and we have added the network, we have added the dense layers. In the first layer it had 5 units and activation is ReLU, and input shape is 28 into 28, and the second layer 10 with activation as ReLU. On the third layer I have 10 neurons with activation as softmax. After that I have defined the learning algorithm to be RMS prop, loss function to be categorical cross entropy, and the matrix is accuracy. And after defining all the model and the compile, that is all the necessary parameters in any machine learning model, I have performed the fit on our data. So I have specified the train images and the train labels for the training, and I have fit for 5 epochs with the batch size as 64. After performing the fit on training data, I have performed the evaluation on the test labels and the test images. So the test accuracy was 86.59%. So this was about our class on building the first deep neural network, guys. So if you have any questions, you can reach out to me at instructor@manifoldailearning.in. For any queries on any of the subject, just reach out to me on this email. Thank you guys. I'll see you next time.